Enthalpy is symbolized as H. It's the total energy of a system at constant pressure. It includes internal energy of the system and the energy required to make room for it by displacing its environment, and that's related to pressure and volume. In chemistry, we mostly care about delta H, or change in enthalpy, and that tells us how much heat is absorbed or released by a system during a process at constant pressure. Thermochemistry is a branch of chemical thermodynamics, and it's the science that deals with the relationships between the heat, work, and other forms of energy. Substances can store energy, and energy can also be removed from them. The internal energy is denoted uppercase U, and it's the sum of all kinetic and potential energies within a system. It includes molecular motion, translation, rotation, and vibrations, intermolecular forces, which we'll talk a little bit more about in another lesson, and electron energies. Intermolecular forces are essentially just the forces that are acting on molecules and between different molecules and within different molecules, or intermolecular forces. As a state function, internal energy is a state function. Its value depends only on the system's current state and not how it got there. And the first law of thermodynamics says that delta U, or the internal energy change, is equal to the heat plus W, which is work. All right, so energy can be transported into a system, resulting in an increase in internal energy. It can be transferred as heat or as work. And again, this is our equation. So delta U is the final internal energy minus the initial internal energy. Sometimes we might write that U sub F for final internal energy, or U sub I for initial internal energy. But this formula captures all of the energy changes that occur in a system. So if a system absorbs heat from the surroundings, Q is positive, and the surroundings do work on the system, and W is positive. Energy can also be transferred out of a system, resulting in a decrease of internal energy, or a negative Q, which means it's releasing heat, and the system does work on the surroundings, so that's negative W. And this figure shows an energy diagram, and we saw a figure somewhat similar to this in the calorimetry example. There's reactants and products on a vertical scale of internal energy, and these arrows are showing heat and work added or removed. The total change in the internal energy is delta U, change in internal energy. And this helps us visualize how internal energy connects to both heat and work. Work is a form of energy transfer resulting from a force acting through a distance. In chemistry, we often deal with pressure volume work, or PV work. For example, in gas expansion or compression, W work is equal to negative P delta V. So that's pressure volume work. Let me see if I can write the formula here. So it would be work is equal to negative pressure times delta V. Positive work done on the system, volume decreases. Negative work done by the system, volume increases. Internal energy, work, and heat. If we suppose a system absorbs 90 joules of heat and does 45 joules of work on the surroundings, we can calculate delta U, or the change in internal energy. So delta U equals heat plus work. So if a system is absorbing 90 joules of heat, then Q is going to be 90. Joules. And the work, if it's doing 45 joules of work on the surroundings, it's going to be negative 45 for our value of W, negative 45 joules. That's going to give us an overall value of 45 joules. This means that the internal energy increases by 45 joules. A state function is a property that depends only on the current state of a system, not the path that is taken to get there. Some examples of state functions include pressure, volume, temperature, internal energy, U, and enthalpy, H. To contrast this, heat and work are not state functions. They depend on how the change happens. To get a bit of a better idea on what a state function is, we can use this real world example of hiking to the top of Mount Kilimanjaro. So this figure shows two paths between the same start and end points, path A and path B, and they lead to the same final state. But Q and W would differ along each path. So regardless of the path taken, our change in internal energy is the same. So it doesn't matter how we get there, it's still the same change in internal energy. Enthalpy, uppercase H. So I've said enthalpy a couple of times so far, but here's our equation for enthalpy. It's defined as the sum of a system's internal energy and the mathematical product of its pressure and volume. So it's the internal energy plus pressure times volume is another way to say that. Enthalpy is also a state function. At constant pressure, enthalpy can simplify to delta H equals QP. This means that delta H equals the heat transferred at constant pressure, which is why we use enthalpy so much in chemistry. Enthalpy change. We're going to talk about enthalpy change more than just in this lesson. So if the change in enthalpy is greater than 0, heat is absorbed. Let me see if this is on some other slides here. Okay. Now, so we'll probably go over this one more time, but if delta H is greater than 0, then it is endothermic. If delta H is less than 0, then heat is released and it is exothermic. We express the change in enthalpy in kilojoules per mole, and the sign tells us the direction of the heat flow. So again, at constant pressure, the change in enthalpy, this is the change in enthalpy formula for constant pressure. And let's see here. This is just a quick proof on how we get that formula. That's a little bit less important. So we're gonna move forward here. Let's see. So delta H refers to the enthalpy of the products minus the reactants. It's measured at constant pressure. Delta H is a state function, just like internal energy, and it simplifies energy accounting for chemical reactions. All right, and thermochemical equations, we include both the chemical reaction and the enthalpy change. So if the work done is caused by expansion or contraction of the heat flow, uh, Q sub P, and the enthalpy change delta H for the process become equal. The sign of delta H tells us heat flow. And the physical states also have to be included. So it's going to tell us if it's gas, liquid, solid, or aqueous. The amount of energy corresponds to the coefficients in front of them. There's also there are important conventions of thermochemical equations. But we're going to talk about thermochemical equations first with an example. So chemists use a thermochemical equation to represent changes in matter and energy. The enthalpy change is written to the right of the balanced equation. So it's just going to tell us what that value is here. Delta H indicates the amount of heat that's associated with the reaction when it's written like that. If we reverse this reaction, that changes the sign of delta H. So if we write this in the other order, it's going to make delta H positive if we write H2O on this side. And if we write all of this on the other side, delta H is going to change the sign. All right, so here's some more conventions of thermochemical equations. We are allowed to multiply on both sides. We can multiply by a factor of 2 on both sides to keep an equation balanced. But when we do that, when we multiply by a factor of 2, we end up with double the change in enthalpy. If we multiply by 1/2, we get 1/2 the change in enthalpy. The change in enthalpy of a reaction depends on the physical state of the reactants and the product. So again, we have to show if it's gas, solid, liquid, or an aqueous solution. All right, so these are color-coded because this is one of the most important parts here. Negative enthalpy means exothermic. Positive enthalpy, greater than 0, means it's an endothermic reaction. So here we have an exothermic reaction on the first example, and here would be an endothermic reaction. And notice that we've just switched the products and the reactants. So these are called the reactants. They're on the left, and the products are on the right. We've just switched those, and that's all it's done is it changed the sign of our change in enthalpy. All right. So let's look at an example here. We have a gummy bear and it has 2.67 grams of sucrose, C12H22O11. And when the gummy bear reacts with 7.19 grams of potassium chlorate, KClO3, 47.3 kilojoules of heat is produced. We want to determine the enthalpy change for this reaction. So the sucrose plus the potassium chlorate, and we're given these numbers in the reaction. We're given the entire reaction. We're also given the grams of sucrose and the grams of potassium chlorate. All right, so now we want to solve this. So here is our equation again, and we're going to write the provided amounts of the two reactants. Now, for this part, we have to figure out what is the molar mass of these substances. So the molar mass can be found by finding the AMU of each of the individual elements on the periodic table, and then multiplying by the subscript. So for carbon, carbon has an AMU of 12, and there's 12 carbons. So now we have so far, just for this section, an AMU of 144. Hydrogen has an AMU of 22, or excuse me, 1, and there's 22 of them. So that we're going to add 22 to 144. And so now so far we have 166. And the AMU for oxygen is 16. And so we're going to do 11 times 16. And that's 176. Add that to the 166 that we had from the carbon and the hydrogen, and that gives us approximately 342 grams per mole. And here, for being exact, it's 342.3 grams per mole. So that's the molar mass of sucrose. And we have 2.67 grams of sucrose. We're going to multiply that by the molar mass, and that tells us how many moles of sucrose that we have. We have 0.0078 moles of sucrose. We're going to do the same thing for potassium chlorate. We're going to find the AMU of potassium, of chlorine, and of oxygen. So if we repeat that same process, we get about 122.5 grams per mole times the 7.19 grams of potassium chlorate, giving us 0.0587 moles of potassium chlorate. So here we have what's called an excess and a limiting reactant. So we need it says since 0.00734, this is supposed to say 0.780. Change that. Since that many moles of sucrose is needed, the sucrose is the excess reactant and potassium chlorate is the limiting reactant. So really what this tells us is we're going to write a ratio between these two values. And so this is 0.0587 moles of potassium chlorate divided by the ratio of sucrose, and we get a ratio of 7.52. So if we round up, this reaction uses about 8 moles of potassium chlorate. So the balanced equation indicates that 8 moles of potassium chlorate are required for this reaction with the 1 mole of sucrose. Since the provided amount of potassium chlorate is less than the stoichiometric amount, it's the limiting reactant, and it may be used to compute the enthalpy change. So what we're going to do now is, since it's the limiting reactant, we're going to write this in terms of it says 43.7 kilojoules of heat is produced. So we're going to write kilojoules per mole is what we're trying to figure out. And we wanted to decide, are we trying to use kilojoules per mole of potassium chlorate, or were we trying to use kilojoules per mole of sucrose? But we found that we want to compare it with the moles of potassium chlorate. So this is not per 1 mole of potassium chlorate. This is per 0.587 moles of potassium chlorate. So if we divide this, 43.7 divided by 0.0587, if we divide that, we get approximately 744 kilojoules per 1 mole of potassium chlorate. Now, because this equation is written the way that it is, that's the change in enthalpy now for 1 mole of potassium chlorate, and we want to finally know how much energy 8 moles uses. So this ends up being times 8, and we get 5,960 kilojoules. So this is our final thermochemical equation. The standard state. A standard state is a reference point that is used to calculate enthalpy changes under consistent conditions. Standard state conditions are 1 bar or 1 atmosphere. That's a pressure measurement. 25 degrees Celsius or 298.15 Kelvin. Solutions are typically at a 1 m concentration, and substances in their most stable form are at these conditions. Standard enthalpy values are based on these conditions as well. The standard state change in enthalpy. The standard state change in enthalpy is change in enthalpy with a degree symbol next to it. It is the enthalpy change when a process occurs under standard state conditions. So those standard state conditions, let me see, make sure. Those standard state conditions for pressure, again, with 1 bar and 1 atmosphere for pressure, or 25 degrees Celsius, or 298.15 Kelvin. Those are standard states. So that's about room temperature for temperature, and 1 atmosphere is just one atmosphere in Earth's atmosphere. The standard enthalpy change is the enthalpy change when a process occurs under these standard state conditions, and the degree symbol indicates that it is standard state and not just change in enthalpy. And this allows us to compare data from different experiments in a consistent manner. For example, the combustion of methane has a standard enthalpy change of negative 890.3 kilojoules per mole. And this applies when 1 mole of methane combusts under standard conditions. It's important to always match your conditions to the standard when you're using these tabulated values. Let's look at another example here. So again, standard enthalpy of combustion would be delta H with the degree symbol, and then we can write combustion is the enthalpy change when 1 mole of a substance combusts completely in oxygen under these standard state conditions. Combustion reactions are always exothermic because they release energy. And these values are often used to evaluate energy content in fuels and foods. The standard enthalpy of combustion, we have an example here. It says that the enthalpy of combustion of ethanol is negative 1,366.8 kilojoules per mole. And this is the amount of heat that's produced when 1 mole of ethanol undergoes complete combustion at 25 degrees Celsius in 1 atmosphere. It also yields products at 25 degrees Celsius in 1 atmosphere. So here it's showing the combustion reaction. So we have our products and our reactants, and it tells us that burning 1 mole of ethanol releases 1,366.8 kilojoules of energy. We also have a table for standard molar enthalpies of combustion, and this lists the standard enthalpy of combustion values in kilojoules per mole for various substances. So for carbon, the standard state of enthalpy of combustion is negative 393.5 kilojoules per mole. So again, this is at standard state at 25 degrees Celsius. And this is an enthalpy of combustion. So this is a combustion reaction, so we use enthalpy of combustion. And we have these values for the others as well. And these values are key when we're comparing the energy output of these different fuels. And we also have values for other common combustion reactions of methane, acetylene, ethanol, isooctane. Let's see here. This figure here, it's just showing a standard enthalpy of formation and combustion, comparing different compounds and their energy content. It's showing the energy is released, which means a negative delta H, and the energy per mole of a substance, it's showing us that as well. So it helps us to visualize how energy content varies across these different compounds. All right, we're going to look at another example here. You just make sure everything is correct on these slides. It's in figure. So from this figure with the explosion and the fire trucks, it suggests that the combustion of gasoline is a very exothermic process. We want to find the approximate amount of heat that's produced by burning 1 liter of gasoline, assuming that the enthalpy of combustion of gasoline is the same as that of isooctane, a common component of gasoline. So we're going to use isooctane as our reference point because it's not going to tell us gasoline in the back of our book. We have to look and look up isooctane. Also, the density of isooctane is 0.692 grams per milliliter. So we want to know 1 liter of isooctane, and its density is given here. We're going to start with that 1 liter, and we can perform these conversions between the units until we arrive at the desired amount of heat or energy. The enthalpy of combustion of isooctane provides one of the necessary conversions that we need. Table 5.2, which is not necessarily in the book that you're reading. There's a table, though, it gives us a value of negative 5,460 kilojoules per mole of isooctane. So you can find that in your book. That's the amount of kilojoules per mole of isooctane. So we're going to do some unit conversion here. We have 1 liter of isooctane. We're going to change liters to milliliters. And that's a simple conversion. 1,000 milliliters are in a liter. So let me color code this red so you can see how I'm crossing everything out one at a time. So liters and liters cancel out. Now we know that there are, let's see, trying to see how yes, the density of isooctane. The density is grams per milliliter. So there's 0.692 grams per milliliter. So we can write that unit conversion next and get rid of our milliliters. Now we need to find the molar mass of isooctane. So we're going to look up carbon is 12. There's 8 carbons. So 12 times 8 is 96. And there's 18 hydrogens. So we're going to add 96 and 18 and we get 114 grams per mole. Grams are on the top over here. So grams are on the top up here. So we want to cancel out grams on the bottom. So we're going to put grams on the bottom instead. So we're doing moles per gram. We're allowed to do that with unit conversion. And then finally, we want to change this to kilojoules. And we know that this is negative 5,460 kilojoules per mole. And so we can cross out moles and moles for our last section of this unit conversion. We can cross that and that out. So we get a final answer of, we multiply everything on the top, and the only term that's left on the bottom is 114, and we get a final answer of negative 3.31 times 10 to the 4th kilojoules. All right. Let me see here. Biodiesel. Okay. So This is a diagram showing the combustion of glucose. So this has to do with cellular respiration. So algae, they convert sunlight and carbon dioxide into an oil that eventually gets harvested, extracted, and purified, and then transformed into a variety of different renewable fuels that we can use. The standard enthalpy of formation. This is delta H with the degree symbol F. And it's an enthalpy change for a reaction in which exactly 1 mole of a pure substance is formed from its constituent free elements in their most stable states under standard state conditions. Let me see if an example. Okay. Yeah. So the standard enthalpy of formation of carbon dioxide gas is negative 393.5 kilojoules per mole. You can look that up in your book, and that's what that value is going to be. Um, so here it shows our reaction. It's the solid carbon plus the diatomic oxygen making carbon dioxide gas. And so the elements in their standard state, like diatomic oxygen or graphite, they have a standard enthalpy formation of 0. Hess's law states that the total enthalpy change for a reaction is the sum of the enthalpy changes for any set of reactions that add up to it. This is useful when a reaction's change in enthalpy is difficult to measure directly, or if there's a series of known reactions that sum to the target reaction. If a process can be written as the sum of several stepwise processes or several individual pieces, the enthalpy change of the total process equals the sum of the enthalpy changes of the various steps. Hess's law is also valid because enthalpy is a state function. Enthalpy changes depend only on where a chemical process starts and ends, but not on the path that it takes from the start to finish. If you reverse a reaction, you reverse the sign of the change in enthalpy. If you multiply a reaction, you have to multiply the change in enthalpy by that same factor. Then you add up all the change in enthalpy values to get the overall delta H change in enthalpy. This approach simplifies complex reactions into manageable parts. For example, we can think of a reaction of carbon with oxygen to form carbon dioxide as occurring either directly or by a two-step process. So we saw this earlier with the change in enthalpy of carbon dioxide as negative 394 kilojoules. But we can write this as a two-step process for the overall reaction with Hess's law. So if we're given these three reactions all together, the technique is sort of like solving a puzzle. So we match the compounds, cancel out the intermediates, and we sum the enthalpy changes. So we want to rearrange and combine them to derive a new target reaction and determine its change in enthalpy. So if we look at this reaction here, we can add up the products, carbon monoxide and carbon dioxide, and we get this value here. And we can add the reactants as well. We have 1/2 of a diatomic oxygen, that just gives us oxygen. And then 1/2 of diatomic oxygen, again, that just gives us oxygen. And we can write those separately here. That's fine to do. And then we have carbon as a solid and carbon monoxide as a gas. These two diatomic oxygens, they become just O2. So cross those out, and it just becomes the O2 here. And now we have a net change of carbon plus O2, gives us CO2. This carbon monoxide gas ends up canceling with the reactants, or excuse me, with the products. The products and the reactants cancel out. So you can sort of think of this as an algebra equation when we're looking at chemical reactions. So we can divide by carbon monoxide on the left and divide by carbon monoxide on the right. So we have an overall net change of carbon plus diatomic oxygen is carbon dioxide gas. Now, if we look at the change in standard state of enthalpy, we can also add those together. So this is the same formula that we had from earlier. It's just not written out in this last step, or this second to last step here. But we can add together the enthalpies to find the change in enthalpy for the overall reaction. And it's the same whether it happens in one step or two steps. This is a diagram that shows multiple reaction pathways. So from that same reaction, we have a direct route from A to C. We could say here's point A. Rewrite that. Here's point A, and here's point C. We have a direct route from A to C. We have a multi-step route, we call this B, from A to B to C. But both routes lead to the same change in enthalpy. And this demonstrates that enthalpy is a state function and that Hess's law holds true. We can also use Hess's law to determine the enthalpy change of any reaction if the corresponding enthalpies of formation of the reactants and products are available. So we can use our standard state of enthalpy of formation tables to calculate the change in enthalpy for virtually any reaction. All we have to do is plug in the enthalpies of formation for all the products and the enthalpies of formation for all the reactants, and then subtract between the two. So when we have the sum here, this is summation notation. This means the sum of, and n is the stoichiometric coefficients in front of that. And we're going to multiply by the standard state of enthalpy of formation of the products. And we're going to subtract by the sum of the coefficient times the standard state of enthalpy of formation of the reactants. Here's what this looks like in equation form. So here's our equation that we have with the summation notation, and we want to find the standard enthalpy change for this reaction. We're given the total reaction here, and we want to find what this value is. We're going to use the special form of Hess's law to find that value. So the number of moles of the products, here's the first section of our products. So there's 2 moles of that. Now, let's go back to our, actually maybe, I'm trying to remember how we, yes. So we need to look in our book to find the standard enthalpy change in state of formation of the product. So we need to look up this value in the back of our book. So it's going to tell us what this value is. So it's negative 207.4 kilojoules per mole of this substance. and we have 2 moles of that, so we're just multiplying by 2. Moles and the moles cancel out. Now we also have another compound that's in our products. We have 1 mole of it. There's just a 1 there. If there's no 1, that just means the coefficient is equal to 1. So now we have 1 mole of that. And again, we'll have to look this up in the book to see what the change in standard state of enthalpy of formation is. And so that's 90.2 kilojoules per mole. Again, moles and moles cancel out. And this is good because now all that's left over is, I'm trying to erase that. All that's left over is the kilojoules. So if we cancel out all the moles, we're just left with kilojoules. Okay, so that takes care of the beginning section of this part here. So we have the sum of the number of moles times the change in our standard state of enthalpy of formation of the products. Now we want to do the same for the reactants. So the reactants, there are 3 moles of NO2. And again, we're going to look up the change in standard state of enthalpy of formation for NO2. And in our book, or you can look it up online, it's going to be 33.2 kilojoules per mole for NO2. And then we look up the same thing for water is 285.8 kilojoules per mole for water. Moles and moles end up canceling for all of these. And now we're just left with a nice equation for kilojoules. So again, we have to multiply though. We had that coefficient. So 2 times negative 207.4 kilojoules plus 1 times negative 90.2 kilojoules. We're going to subtract now the reactants. 3 times 33.2 kilojoules. And this is a little interesting. We have this plus this negative here. Let's see what's happening. So we have this minus happening here. If we subtract it all, we would put parentheses like this, and we would write the plus like that. But if we're distributing the negative here, and I go back here again, eraser, if we're distributing our negative sign there and to there, that's how we get this final answer of that negative 1 times negative 285.8 kilojoules. We get a final answer of negative 138.4 kilojoules. And again, this has to do with Hess's law and finding the standard state of enthalpy of the reaction. And we're doing that with the standard state of enthalpy of formation. So the formation is going to be, they're going to tell us what that is in the book, and we can calculate the reaction by using the formation values that are in the book. All right, and here are the practice problems associated with this section.